Oh my gosh, now where am I? No. What in the world? I checked. Can everyone hear me? Why wouldn't you be able to see me? That's weird. Oh, I know why. Oh, I think I know why. Because I brought up OBS to see if I could fix it. Everyone can see me, but you can't hear me. Okay, so I'm gonna reset the camera real quick, Ali, then we'll go back. So I think because I brought up OBS, I think OBS took the camera input. I don't know if resetting the camera is gonna fix it. Because there was an issue when I tried to stream to YouTube. It like didn't go through. Everyone can hear me, but you can't see me. So we might do no Brian visual today for this, and I'll have to restart the computer. But I brought up OBS for a second because I'm using technical stuff. But when it wouldn't stream, and then it did stream, I was using Streamlabs, and so apparently OBS might have took the input, and then you can't send camera input to two things. So let me turn on and off the camera real quick. Let me go to a non-camera scene. So let me go to scene without the camera. We're just gonna go to one without the camera. Without the camera. Okay, I'll be right back. One moment here. Okay, I'm back. Let's see here. Okay, did it work? Did it work? It's gonna take a reset here. Okay, so I won't be on camera for this, so I'd have to reset OBS and reset the stream. So let's not go full reset stream. No camera today. No. Okay, so you'll have to do this without seeing me. Okay, let me bring up the document here from yesterday. Oh no. Okay, so one moment, we're bringing up the assignment. Ali's first question is, I can't see me, I'm looking at everybody. No. Okay, so Ali's first question is, when we do regression, there's a really good thing right here. So I need everyone to be super interactive since you can't see me. So when we do regression right here, how do we know the significance of the model? So the first question was, how do we find the p-value of the linear regression? So it's a really good in 201. Unfortunately, you just had a test on this, but a really good review when we have a we have a linear model right here. Oh, we have no linear models. Let's make one. So let's go ahead and make a linear model. I'm going to use Survey 10 to do this. So I've already got some Survey 10. Look at that. There we go. How do we know the significance of a model? So let's put this in here. I'd have to restart the stream to get the camera back because it's, I wonder if, no, turning the camera source on and off is probably not going to do that. How do we know the significance of the model? How do we know? Who knows? How would we know the significance of the model from the top? But there's two ways. And I'll show the trick here in a moment as I look for my camera source. Okay, I'm going to go to the camera source and that didn't do it. Didn't do it. Have to reset Streamlabs. I'm going to reset the computer after this probably. How do we know the significance of this model right here? And so when we think about the significance of the model, what are we talking about? For linear regression, yeah, we can do that next, Bailey. You got it. Sorry, I can't see anybody today, or you can't see me. I will definitely have this fixed for class. How do we know the significance of the model? How do we know exactly in which there's a few p-values, Kayla, and there's one wrong p-value, and I'll show you something very important right here. There's one wrong p-value, and this points to it. Think about studying and grade in the class. I always use this example right here to think about, we try to keep examples in our head to remember, like, which p-values should we be looking at? And there's a lot of mathematics here. Like if you start really looking into it, you'll see some really interesting relationships to this. Like I can do in my head, if you're ever wondering, I can do 19.9 squared, but that's kind of too easy because it's very close to 400. 19.9 squared is 394. So if I do 19.9 squared, that's 394. Oh, wait, what? Oh, it's because it's not carrying all the decimals. It has to be smaller than that. Let's go look at the options digits. I should have known when I rounded it to that. So let's put the digits to 9, and let's put the SciPen to 9. Let's put the output up here again, and let's talk about which things. There we go. I meant to say 19.8544 squared. That is going to be 394.19. There we go. That's what I thought. There we go. Look at that. The square of the t statistic is the f statistic. Now, why am I showing you this? The square of the t statistic is the f statistic. So most importantly, and so Kayla, which p-value are we going to look at? Because I just mentioned how the square of the t statistic right here, this t statistic, is this f statistic. And I think it might be easier to understand this if I do a model that's way less significant. So I don't think I have these attached yet, so I can't run them easily. So which p-values should we be looking at? Oh, I did have them already attached. So let's go right here. Text per day. Exactly. And so this model makes it clear. So when you look at this p-value right here, this is the p-value of the t statistic, or the p-value of, it's all the output right here. This p-value is in line with this output. It's the p-value for the slope of the line. And we actually really care about the slope of the line. Think about studying in your grade. The slope matters here. The intercept does not matter. It doesn't matter where the intercept is at. This test up here says the intercept is not 0, but this test down here says the slope is not 0. It's less significant than the previous model, but you can also see from this that it has the same p-value as the whole model. So this is the test for the whole model. When we start doing multiple regression, this will come into more play because we'll have more x variables. But right now, there's only one x variable, so that x variable has the p-value down here. So we could also take and square this. And if you square this, this squared is almost exactly 5. It's almost the exact square root of 5. And how do I know that? It's the f statistic, which also confirms for us this bottom portion of the output right now in the simple linear regression is the same here. So the significance of your model is the significance of the slope right now, but it is worth noting. So here's a big note to take. The significance of the model in multiple regression will not be the slope itself. What will the significance of the model in the multiple regression be? And then I'll mention why this is the case. What is the significance of the regression in the multiple model? What is the significance of the regression in the multiple model? Oh no, and to get r squared, we would so here's the r squared right here. And if we square root this, we get correlation. So that's the correlation for this. Like if I were to run, I'm trying which variables we had. If we were to run correlation on these, I so rarely run correlation. They are both in the goal environment. I think it's a negative yeah, it's negative. You have to look at the graphic there on the right. Wrong syntax. There we go. So it's negative, and that's the correlation right there. Yeah, no worries, Ali. These are great questions. Like, I wish you could see them. Like, yes, keep on. Let me throw some 50 points. You can't see me today, everyone. These are the questions people need to ask because then it's like, oh, yeah, I get it. Yeah, that's it. Would you use the multiple or adjusted r squared? So the multiple r squared is your r squared. The adjusted r squared is the r squared adjusted. It is r squared with a penalty, and it's for when we make multiple models. So I'll explain more about this in multiple regression. But the reason we have an r squared adjusted is, think about this. What model would have a better time explaining, or an easier time explaining, a model with 100 variables or a model with one variable? Like if you have a model that has 100 x variables or a model that has one x variable, which of those has an advantage? Like would probably do better? Like I'm not even saying what the variables are, but one model has 100, or the one with the more variables, right, Ali? So the model with more variables would have an easier time explaining. So because of that, we do what's called an adjusted r squared, which puts it on an even playing field. So this adjusts the r squared based on how many variables are in the model. And notice what happens with the adjusted r squared. It's actually lower. So here's a really interesting thing. I'm going to do something real quick. I'm going to make, let's go right here. Sure. It doesn't really matter where we go. So adjusted r squared is a really important topic because I didn't realize this till way later on. Here's x going from 1 to 100. I mean, y. Now we're going to do x1 is random normal numbers, 100 of them. And oh, no, can't do that. Okay. So any relationship between x and y right now, because these are random normal numbers, should be what? Any relationship between x and y should be what? So any relationship between x and y with what I'm creating here should be what? Because these are random normal numbers. If you were to hand this off for r squared, which value would you square then, since it isn't the p-value? There's no value in our output currently to square to get r squared. We don't currently have a value. Yep. We would think that this is completely random. We'll call this model 2. We have y tilde, and this is how you do a multiple regression. You just do plus, and we'll change the x's this way. So all you do here is plus. And then we're going to change the numbers on the x. So this is now a multiple regression. We went to 12. Oh, I almost did it perfectly. There we go. And what I'm going to do first here, before we do this crazy multiple model, I'm going to go here and take just this model. Now let's look at them. Okay. So these models are only by random chance. The p-value should be very what for these models? The p-value should be very, very what for these models? So we think it will be this. It doesn't have to be this. There's the model. Looks kind of flat. It could have looked flatter. But the p-value for this should probably be pretty what, because this is actually due to random chance. Now, we could luck out, and it might not follow the trend 5% of the time. But probably, since it was created by random chance, it's probably going to have a very what p-value. This model is completely by random chance. For example, number 4, mathematically solve r squared and interpret its value. Yeah, I'll show you how to do that right here. That might have been what Ali was asking. I'll do this a little quickly here. It'll be very high. Good job, Leah, right there, and everyone. So it'll be pretty high. Let's take a look. And the p-value is pretty high. It's high enough. Now, when you look at the r squared right here, r squared is 1.8% of the variation. It's actually due to random chance, or we think it's due to random chance, like it's likely due to random chance. The r squared adjusted is this. Now, this model has an advantage. What will be higher for this model for sure? The r squared or the adjusted r squared? This model with more variables in it, more x's. So this is the percent of variation explained, and this is the percent of variation explained when we penalize ourselves for how many variables are in the model. Which of these will be higher for the second model right here? So we have the percent of variation explained and the percent of variation explained after we penalize ourselves for how many variables are in the model. So which of these will be higher for the second model? The multiple r squared, exactly. So that's higher, but what do you notice? And I'm so glad it happened. So now we're up to 11% of the variation explained because I added in a whole bunch. We went all the way from 1.8% of the variation to 11% of the variation. But after we penalize ourselves, and this is why this doesn't have an interpretation, after we penalize ourselves, the r squared adjusted is now what? And look at the p-value for the model. P-value for the model is even worse. So you're like, whoa, we got 11% explained just with all these random variables that are complete junk variables. And one of them, none of them are actually statistically significant. They're all junk variables. The intercept, no one cares about the intercept. That doesn't matter. That's just a random point. So the r squared adjusted is negative. We don't interpret it as a value. We just kind of say, well, you know, like I know this is still interpreting it, but it's the percent of it's the r squared after we've adjusted for how many variables are in the model. And it's 100%. This whole model as a whole is not statistically significant. So it hits upon the point really quickly how all of this right here are the significance of each x in the model. So when when you have a multiple model, you want to look down at the significance of the whole model to figure out if all of these x's are significant. In the previous one, the singular x, this loops back to Ali's original question. In the singular model, in the simple model, we see that the significance of the 1x is the significance of the model. Multiple model, you have to go down here because there's multiple x's. So this is no longer the significance of the one variable, which it is in the simple model. So the question about the ANOVA, let's use this model right here and calculate the r squared from the ANOVA. That's a little bit, it's pretty crazy right here. So let me ask you this. Just if you understand how the ANOVA works, which we cover, no, I can't remember which day we covered. I think we covered it yesterday, and we'll cover it today for today's class. So when you look at this table right here, there's a lot going on. We haven't talked about sums of squares in today's class yet, but sums of squares, I'll show it visually. Well, we probably still have the drawings up from yesterday. So the sums of squares, might work better if I draw it. Here's the sums of squares. These red ones right here are from the naive model. And we actually don't have any error on our model. So what you want is you want this right here. You want your model, this line right here, to have no error. And so it has no error. But we don't usually get this. When we talk about a sum of a square, we oftentimes moreover see something like this. This is what a sum of a square is. We see a model that looks like this, and we see the points. And here's what the sums of the squares would look like. Now, if each of these are 3 by 3 squares, yeah, we covered this yesterday with Kayla. So if each of these are 3 by 3 squares, like what I'm saying here is this has a positive 3 residual, this has a negative 3 residual, this has a negative 3 residual, this has a positive 3 residual. What would be, and this is an amazing test question, we need to make a test question section, but what would be the sum of the squared error right here? So what would be the sum of the squared error for this model? What would be the sum of the squared error? Only time could you work the... Yeah, let's do that. We'll do that. You got it, Lydia, right there. You got it. After this, we'll do that. What would be the sum of the squared error? 36, exactly. And the way we're getting that is we're just squaring all of these and then adding them up. And so what you want is you don't want the residual error right here. The goal, which you rarely get, is all your points are directly on the model, because then there'd be no error and you'd have 0 sums of squared error. But we have this sums of squared error, which is going to be the error our model has. So this is the residual. This is sums of squares residuals, which is from our model, is 36. But we could also have the naive model, which we'll cover in today's class. And the naive model is going to make more error. It's going to make 5 on this one, and it's going to make 4 on this one, and it's going to make negative 4 on this one, and negative 4 on this one. So what, oh, yeah, that's fine, good. What is the sums of squares total? And we're going to calculate R squared from this. This is a great test question, probably one of the hardest ones I can write, but it explains how this is the total variation that exists from the mean of y, which is the naive model. And that's a big concept to know also, that the naive model is the mean of the y variable, like if you average all the y variables. So all we're going to do is literally, as people are computing the answer, we're literally going to just take these and square them. And so you would just square them right here. And it should be 16 plus 16 plus 16, 48, 73. Great job right there, Kill. Let's throw some 20 points, everybody. Kill, you are 100% right. It is 73. I'm doing it in my head too, making sure we have it. So it's 73. So that's the total variation that exists. And you know what's really interesting? You can tell here that R squared is going to be very close to what with this? Because what we want to look at, and we cover this today, is the sums of squares total minus the sums of squares reduction. I mean, no, that's not reduction. That's the residuals. Sorry. And this is on top is the reduction the model has. This is how much we've reduced the total. And so if we plug in these numbers, we can actually solve for R squared. And we've done it mechanically right here. So 73 minus 36 over 73, and R squared is 50.68. That means we've reduced the sums of squared errors by 50.68%. And you can imagine, as we saw in the previous examples, if all the points were on the line, there'd be no error, and we've 100% reduced the error from the naive model. So when we look at our model right here, or the data we have, this one's a little too complex than I want to deal with. This right here is the variation that the x variable is explaining, and this is what it's not explaining. This is the residuals, what is left over. So it's going to be way easier to compute instead of this one for this one. Let's go ahead and take a look at this output and compute the R squared. And let's think about how this works. So this is directly like your question, but with just different output. So our model either explains something or does not explain something. our model either explains something or does not explain something. If you add these together, you'll get the what variation. Our model either explains something or does not explain something, and there's variation to explain. So remember back from the example here that our model will either explain something or not explain something. So we have a what amount of variation that exists right now. Like either our model explains the variation or does not explain the variation. If I take both of these and add them up, what will I find if I take both of these and add them up? If I take both of these and add them up, well, I get the total. Exactly, Ali, great job right there. This would be the total. So if I take both of these and add these up, this is actually the sums of squares total. So with both of those added up, this is the total variation that exists. Now, residuals sounds like what? Residuals sounds like what? Which, if you look at my mathematics previously, it's actually on here. So the residuals sound like what? Because we can actually solve it this way mathematically, which is all right to do if you solve it this way. It actually already gives you the next step. It actually already solves for this up here. So the residuals is the what? It's going to be from the regression model. Great job. Good to see you here, Jackson. So the residuals are this right here. This is what's not explained. So you could use my direct formula that I just gave where I did SS total minus SSR, what's in the residuals, and divide that by SS total. And wait, what? What did I do? Oh, I did equals. Oh my gosh. There we go. There we go. Like, what is going on? But interestingly enough, this portion right here, how much did I miss by? Or I just made an error. This portion right here, this reduction is actually where? Does it make sense what the reduction is? The reduction is actually in the output. So when you take this portion right here, the sums of squares total minus the sums of squares residuals, because this is what's in the residuals, you're actually getting this portion right here because you have the total is what your model explains and what your model does not explain. Who here thinks they understand decently what's going on? I know this is a big concept. Like hopefully with walking through it right here, we see we have a total variation from the naive model. That is the total variation that exists with both of these added up. We have what our model does not explain, which is this right here. So that would be, it's a much smaller in this example. In our model, it's the portion that's in the green right here. That's what our model does not explain. This is for 320. Yep. This is the complex stuff. We do some really, like we go much deeper into regression. So the sums of squares total minus the sums of squares residual, the sums of squares total is equal to r squared. That is correct. And that's what we have right here. So we kind of drew it out. But the top part of this right here is also known as the reduction. Because what do we want to do to the error? We want to do what to the error? And you can see the reduction is this value right here. That's the reduction. And we want to minimize the error. So this is what r squared is literally doing. R squared is the percent of variation that we've reduced the error by. So does that make sense right there, Ali? It's don't worry, like I don't say it lightly, like this is like the pure mathematics to solving r squared. So we have error from the naive model. That is the total error that exists. That's this red line right here is the error from the naive model, which is the mean of y, the no knowledge model. And then we have how much our model misses by, which is the green model here, and that's the residuals. And then we have the reduction right here, because what is r squared? It's the percent of variation explained. And what would we like? We'd like our model to be perfect. We'd like our model to reduce the error 100%. Because in this model, great job, Ali, excellent work. I'll draw right here this, but there's no error in this model. So our model has done what? R squared is what for our model? Because if you think about this mathematically right here, you'd have maybe sums of squares total 74. That's just made up. And there's no error in our model. So mathematically, you'd get that we've reduced all the error, the top part being the reduction. Does that make sense for this little mini example down here that there was 74 error? That's just a theoretical number, just made up. And then our model has no error. So we've reduced 100% of the error that exists from the naive model. So if this makes sense, yep, it'll be 1. Yep. So if that makes sense, hopefully it shows how r squared is the reduction in the sums of squares error that exists in the model, which is variation explained. So that's why we say blank percent of the variation in y is explained by the variation in x, or later on we'll just say our model, because our models will get more complex. Was there any other 320 questions I missed? But this is really good. This covers, I think, task 2, is it? Because there's only 3 tasks, and we did conference roles at the end of class yesterday, and we'll do them at the end of class today. But this is how we get it. If you're wondering, someone might be wondering about the last one, the other problem I did, we need to go model 2. This one is way more complex. To get the R-squared on this one, to get the R-squared on this one, we need to take all of these right here. Or we could just take what's left in the residuals. We know the sums of squares total. Oh, cool. We can take our sums of squares total from the last model, and then we could take the, so let's just say sums of squares residual 2, and there's the residuals. So we could take the sums of squares total minus the sums of squares residuals 2 over the sums of squares total. Make sure to put things in parentheses that belong in parentheses. And there's the R squared, and we'll show it. So luckily, because of our last model, the sums of squares does not change, and we have done it. So that was, yeah, let's do conference roles real quick. So if anyone noticed, we were able to quickly get it for the second model since we already knew the sums of squares total instead of computing all of these. And then we have what was left in the residuals, and then we looked at the reduction. And this is the reduction right here. Like all of these added up is the reduction. Does that make sense, Ali and everyone else? Like these are how much each variable individually are reducing the sums of squared error. So I can just figure out the reduction by doing 1 minus the total. And that's what I believe I did just a moment ago, is I did 1 minus the total to get the reduction. Or, yeah, I'm doing that right here. So here's the reduction up top. So all of those added up would be 9,179 if I were to add up all of these right here. This is about as complex as I can get, and we did a little bit of multiples. That's awesome. So to get the confidence intervals, so this is confidence interval talk. Number 3, confidence intervals. Okay, to do confidence intervals, we just need to type confident. Now, be very careful. We will have something else later on where we do predict. And is it interval? I can cheat and look at it. Oh, it is lowercase c. There we go. There we go. We will have this later on. And let me show the differences right here. I'm going to differentiate between the two of these. And I've just seen throughout the semester people get very confused on both of these. So confident, which is the one we're using. Let's look at our model. Cool. Our model is predicting what? Very important we know what our model is predicting. Our model is predicting what from what right now? Our model is predicting what from what? So we need to know what our model is doing. It's up here. And let's just make sure we understand what the model is doing, because I do supply output like this on the test, and I might ask questions like, this model was made to do what? So understanding the output and being able to communicate so much I can't do today. I can't communicate. Understanding the output and being able to communicate it is key. So this model was made to predict what from what? Height from text per day, exactly. So when we look at this, what confident does, confident is going to give us confidence intervals for the whats. So just put this in your words. Great job, Ryan. So, and Kayla and Ali. When we see confident right here, I want you to put in your own words what confident is doing. Confident is doing what? The function confident gives us confidence intervals for whats. Confident gives us confidence intervals. It's on a new line right here. What does confident do? So look at what we have output wise. So here's the output for the summary, and here's confident. Confident, I guess it might be, no. Yeah, it can't be that. I wish it was this. I wish it was cofins. I wish it was cofins. Creating confidence intervals not for the p-values. Great, and Kayla, good thing to point this out here. We did do confidence intervals for p-values before. These confidence intervals are not for the p-values. So when we first did confidence intervals for the estimates, for the coefficients. So the coefficient estimates. And that's so great. I'm so glad to see that right here. And great job, Ryan. this is what you need to see. And if you're like, oh, okay, it's giving me confidence intervals for these estimates right here, and we can kind of connect the dots between these. Just kind of seeing this and making sure it's connected in your head that confident is a function that gives you confidence intervals for the estimates in the model, the coefficient estimates. Like I'm saying, I think this intercept could be between these values. Does that make sense when you think about it? Like the intercept about 68, but it could be as low as about 67.6 or as high as 68.4. The slope is about that tiny number, or it could be about this tiny number to this tiny number. Like I'm making a plus or minus. I wish you could see, like with my hands, I'm trying to be like plus or minus. You can't see today. But this is the interval I think the slope might be in. I'm saying like, I always do it. I was like, you'll see yesterday and today, I'll like bend my arm and be like, this is the slope, and I'll move the intercept. This is the intercept maybe. It's the uncertainty based on the standard error. And I want you to do 2 times 2 in your head really quick. This is a thing we'll talk about a lot today at the end of class. If you do 2 times 2, you should get 4. And look at this. Stat 201. Brian has just made, by going up 2 uncertainties, what have I made? And by going down 2 uncertainties, what have I made? So if I go up and down 2 uncertainties, what am I making by going up 2 uncertainties and down 2 uncertainties? By going up and down 2 uncertainties, I'm saying like, here's my estimate. I'm going to go up 2 uncertainties, and then I'm going to go down 2 uncertainties. So what am I making by going up and down 2 uncertainties? What am I making? I'm making confidence interval. What kind of confidence interval? Because basically, and take a look what's going on right here. We can use this screen from 201. We can use their work to say we had an interval that was centered at 68 with an uncertainty of 0.2. New 95% confidence interval, right on. Nice job, Ryan. We're making a 95% confidence interval. So what if I were to run, so look at this screen. If I were to run a 68% confidence interval, I want you to give me the values when I run a 68% confidence interval. And these are test questions. These are test questions. If I were to make a 68% confidence interval, what values should appear on the screen? Very close to these values should appear. If I run the code for a 68% confidence interval, it should tell me the intercept could be as low as this, or the intercept could be as high as this. Like we're 68% confident the true intercept is contained in the interval blank to blank. And this interval is going to, I'll give away the answer a little bit. The interval is trying to estimate the true intercept. So it's saying we're 68% confident the true intercept is contained in the interval blank to blank. So this is an interval to estimate the true intercept. So if I were to run this, and it's very easy to change the code to run for a 68. Usually run 95 because 95 is classic, because it really still 5% off a level. Exactly, Ryan. Great work. So when we go over here and we run confident on it, and we change the code just slightly to say level, I believe the argument is level, equals 0.68, look at that. Look at that. You're within decimal place accuracy. So you were able to figure this out without the usage of the code, because all you're doing is going plus or minus 2 uncertainties. The standard error is this. So it relates exactly to what we do in Stats 101, where we just go up and down. Where's that beautiful graphic? No, is it? I need to memorize which one it is. I'm so just skip. There it is. I knew it was around there. It's going plus or minus 2 uncertainties. So I could take this same exact thing. We're just going to go wacky right here. It's not Wacky Wednesdays anymore. It's Throwback Thursdays. So if you notice now, here's a 99.7% confidence interval. And we did round our numbers, but we should get something close to 67.4 to 68.8. And we run the code again, but we just change it to this. We go right here and change the level right here, which controls the percent confidence. And now we get 67.4 and 68.6. And that is almost identical to what we said we should have. 67.4, 68.6. And just so you can see, oh, the top one is off. Wait, oh, did I get my mathematics wrong? I was like, I have no idea why it's that far off. No one called me out on it. I was like, that's really off. Brian can't add. Sometimes I have so many tabs open, I have to scroll down in Word. But I was like, something's wrong here, because I was like, this shouldn't be that far off. So now 67.4 to 68.6, because the standard error is 0.2. And there you see, 67.4, almost to the decimal, 68.6. And that's because the standard error was about 0.2. Look at the numbers I put right here. I put the estimate, and then I'm just using the standard error. I hope this helps right here, seeing that I have my estimate at the center, rounded, and then I have the standard error is the up or down, and then all I'm doing is the 68, 95, 99.7, and you can choose any confidence interval you want, which we can choose ones that are not on there. We could do like 98, and it'll give us a 98% confidence interval. So Confident gives you confidence intervals for the coefficient estimates. The only other thing I want to point out here, and they'll probably do some 201, is the prediction right here. So what is the deal? What's the deal with the prediction interval? Prediction interval and confidence intervals are these. Now be very, very careful. I'll show you what they are visually. A prediction interval and a confidence interval are, let me remove that. Oh, it actually tells you, so we may should keep it on the screen. So if you notice right here, it says prediction interval and it says confidence interval. Now the confidence interval is for the slope of the line. This is the mean of the y given some x. So this is the confidence interval for the slope of the line. The prediction interval is for individual points. So if I were to say, let's predict for somebody who texts 600 days, I would predict their height is between this and this. And I want you to notice something about this. So Terry Higgins has not emailed me back about a way to complete the question that messed up on the exam. Oh, yeah. Jackson, no, we're actually, I was emailing Terry about that this morning. I think you emailed me and then I emailed us with Terry. So we are finishing that up. The exam was Tuesday, and thank you so much. There was an issue with a residual question that actually had the wrong answer. And so I was just like right before stream, I was doing some emails and sorry, you can't see me visually right now. There was stream issues. But let me just say, I can say pretty much it looks like I'm going to probably be correcting the questions. I'm just putting that out there because I really believe we should be correcting it. I don't care how much time it takes. Things got to be fixed. And then also, it looks like we're going to do like a curve / bonus. But Terry's the stats one coordinator. But to me, I just can't imagine not correcting the question because there was a wrong answer that was right or right answer that was wrong. So Jackson, thank you so much for pointing that out. And we are definitely, Terry and I were emailing this morning about it. So I think we should know, I'd hope I can say something today about it. I mean, I have right now, but I hope I can make it more official. This is what everything has been planned out. But Jackson, thank you so much. And we're glad people like notice things like that. Luckily that was the only major issue. It's sometimes I hate it. We've had worse issues with tests. We've had like where one time the printer like didn't print the pages for people. Oh god. We've had we've had where like people didn't get full tests. And it's like, what happened? It's like, oh, the printer didn't do the front back. And we had where the printer didn't print the numbers legible. You couldn't read the numbers on the test. That was a fun test. 11 years of Stat 201. I can tell you all these stories. Oh man, craziness. So here's a really, Kayla, Ryan, I might switch to 201 in a second here, but I want to I want to show everyone something in 320, something really interesting about this interval right here. I can estimate something from this interval. So Kayla, Ryan, Ali, are you still here? And I'll show you a trick and it'll help with this assignment. So let's see. It'll be a trick that'll help with this assignment to maybe better understand the concept. I might just mention it. Oh, I feel so bad. I hate that no one can see me right now. This interval right here, this prediction interval is for the individual points. So this is not exactly how the interval is calculated. It's not calculated exactly this way. But I'm going to look at this and see that it starts here at about 59 and goes up to 67. Yeah, it's about 68. So that's 59 to 68. So that's 9. The length of this is 9. And yeah, that looks about 9. I'm going to take half of that and go to 4.5. And I'm going to say, usually about an average miss. About an average miss here. Like if I were to say like, about halfway here, about an average miss is about 4 to 5. Like we usually miss when we predict somebody's height by about plus or minus 4 to 5 inches. What have I just kind of estimated using the graphic? If I were to say, so I don't know if any 320s are listening to hear that, but I'm saying, and this is part of this assignment, I'm saying we usually miss, and let me put a note right here. Well, It'll give away the answer when I put the note to remind myself what to mark this video. So let's say here, using prediction interval to estimate RMSE. So we usually or typically miss by about 4 to 5, or I'd say about 4.5 we miss by. And let's look to see if my estimates were good. And the answer is, where is it? There we go. My estimate was 4.5. Remember, if you check the video, no, you can't check it. My estimate was about 4.5 because this is the residual standard error. And this interval right here, from the red line down to here, is about 2 residual errors. Exactly. Does that make sense, Kayla? Because I'm like, usually when we miss predicting, and I hope that helps make more sense what the residual standard error is, because think about this. The residuals are these. These are the residuals. And then the standard error is our uncertainty about how much we could be off by. So the residual standard error is the kind of typical miss of the residuals. Even more so, the residual standard error is calculated by the root mean squared error. So when you cancel these words right here, you just get mean error. Now, the reason we don't use mean error is because, as Stat21 knows, all the residuals would add up to 0 if we just added up the residuals. So we do root mean squared error. We square it to make them all positive, but we root it so it's back in the units of the problem. That means we're basically doing a mean error, like a typical miss that the residuals have, which we wish we could just do. But once again, if you just do the mean error, it would be 0. So you square it to make them all positive, and then you root it to put it back in the units of the problem. There is an alternative known as MAE, which is mean absolute error, and the absolute takes away the problem of some residuals being negative. Because remember, they will add up to 0 if you add them up, and they would mean to 0 if you did the mean of them. So both of these are just trying to figure out a way to talk about the typical miss the model makes. And this interval right here is generally about 2 RMSEs. So that means this prediction interval right here is a what % prediction interval. This is a great question for the test. Since this prediction interval right here is 2 RMSEs, this is a what % prediction interval. So RMSE is residual standard. Yep, same thing. Great job, Kelly. Yep. RMSE, root mean squared error, is the residual standard error. You'll hear me use them interchangeably. You are 100% correct. Yay! And this one is 2 RMSEs. So since that's 2 away, basically like kind of 2, the formula is a little bit more complex than just going plus or minus 2 RMSEs. It's got corrections in there for how far it is away from the mean. We'll see the formulas, but I let the mathematics do the fine work. Exactly, Ryan. It'll be a 95%. And if you look at this, does it look like 95% of the points or so? Because I only see those points right there, and there might be a few up top. I'm going to make that thing go away. Where is it? You have to go loc equals that. Okay. Does it look like about 95-ish% of the points are contained within these intervals right here? Like there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 points out of how many? So n row, we could do this. So 11 divided by n row, this is survey 10. That's more than 95. Maybe we're missing, like the way Dr. Petrie does his thing, you miss some points, which is a big bummer about it. One last check. Plot, we're plotting height. Because I bet you there's some points outside of that. Yeah, you can see points down here that are not in his plot. So there's another 1, 2, 3, 4, 5, 6, 7. There's another 7 points. So with another 7 points, we don't reach the 95, but we get a lot closer. So with another 7 points at least, it would be 97.4% or so. So 97.4%, which generally speaking, we would expect 95. And maybe there were some points close to the line that I missed. Like maybe there were some, like maybe that one, or maybe I missed counting some of those. But it's about 95%. It's close to, and we expect 95% intervals to contain the truth 95% of the time. 95% of 95% intervals will contain the truth 95% of the time. Doesn't mean all 95% confidence intervals will contain the truth. It just means, yeah. So it's a long run thing, law of large numbers. Any questions? I think we can do one. Let me do a 201 question that we don't have a video for. I don't think I have one for the kids, which is a deceptively easier question than it seems. So I don't think I have a video for the kids question. And so let me bring up tool 1 right here. And thank you, 320. Excellent talk, 320. I hope this explains everything. The prediction interval thing right here is actually making, right now I'm making this confidence interval for the mean. And if I do this, that'll be a prediction interval for all the points. So if you notice, this is wider. We'll cover this in the second part of simple linear regression. This is not on this assignment. This one right here, this code that I'm showing on the screen right now, this code makes these intervals, and this code right here makes intervals for the estimates of the coefficients. So the code I am highlighting makes intervals for the estimates of the coefficients. This code right here makes these intervals. I want to make sure this is clear, and I'm going to put a note. So difference between two confidence interval codes. This is where people get vastly confused with the test and everything, is that this code right here, the prediction interval, uses the line of prediction and then either makes a confidence interval for the mean based on the point we're predicting, or makes a prediction interval for the individual. So I'm doing confidence interval for the mean right here, so it's making this interval the tighter one. But if I were to change this to prediction, then it would make the prediction interval for the individual. This code right here makes confidence intervals for the coefficients of the estimates, and we can see this if we run it. We're going to get a confidence interval for the true intercept, and we're going to get a confidence interval for the true slope of this line. It's still doing it for the line, but the ones you see visually on the screen right here, this interval right here, this black interval, and this dashed interval, this is the confidence interval for the mean of the line. This is the confidence interval for the individuals we are predicting for. And this output right here is going to give me estimates or confidence intervals for the estimates. So hopefully that helps differentiate the two codes. There's a lot of confusion when we get to this about, wait, confident does what and prediction does what, but big stuff right there. Let's do the family having children. Lydia, thank you so much. I'm going to have to reset the camera. I brought up OBS because Streamlabs was just so weird. When I brought it up, it like wasn't streaming, and it said your stream was disconnected 18 hours ago. And I was like, that's weird. I need to like look at my video to see, did I like not turn off this? I don't like it when Streamlabs says weird stuff. I don't like it when Streamlabs says like, your stream ended 18 hours ago due to disconnect problem. I'm like, I was not streaming. Was it birth defects question? I think this is the one that Lydia wanted us to do. And this question right here is pretty tricky. So let me double check her question to make sure. Only if we have time at the end, could you work the baby with, birth defect one, birth defect, babies with birth defects. Here we go. So it's the babies, there's multiple baby questions on here. Baby with birth defects and lottery with lucky number 1 question. Yeah, lottery with lucky numbers. Okay. So with the babies with birth defects question, a study finds out that out of every 300 babies born in the world, 9 have some kind of birth defect. What is the simplest way to assign random numbers? So when you think about this right here, we have 9 out of 300. So how would we assign random numbers when we solve this problem right here? Well, we know that 3% of babies are going to have birth defects. So if you were to make a number line, a very long number line, which is really easy to do in R, we could go through here and go from 0 to 99. So here's our number line. Ignore this on the left side. I'll make it even easier to ignore it by doing the following. So here is our number line of numbers. This is one of the many reasons I love R. If I could get the window to go bigger. So we have our number line. Our number line goes from 0 to 99. Now, 0 to 99, a lot of people get confused by this, but you can tell how many numbers it is if you start at 1 and just count to 99. Like, it's confusing at first, and then you go 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way to 99, then you get back here to 0. This is 100 numbers. Now, you might be saying, why would you do this? Well, a lot of random number tables will have the following. Random number tables usually look the following way. They'll have random numbers here like this. So this is a random number table, just complete randomness as best we can do. And so with this random number table, you could select 2 digits to start. You could start here, and this would be 20, this would be 39, this would be 80, and if you got to a random number like this right here, this would be 9. So the reason, I think we maybe got that, we could start putting commas. Did I do it? Yes, I did it. This would be 9 right here if we do 2-digit number combinations. And that's why people often use 2-digit numbers instead of going 1 through 100, because with a random number table, you could have here 20, 39, 80, 23, 09. So maybe this might not make it clear enough, but this would be 00, 01, 02, 03, 04, all the way to 99. And that's why people often use numbers like this. So we can use 2-digit number combinations. So that would represent 0 right there. And this would represent 99 if we came across this in a random number table. So that's why we use 2-digit number combinations as is being used in this problem right here. So we're going to use a 2-digit number combination right here. We're going to use the digits between 00 to 0 what to represent birth defects. Now remember, we said there was a 3% probability of birth defects, and we have 100 numbers. So be very careful. Start counting here. We would have 0, let's go to the numbers. We would have 00, 01, and 02. I think that's where people get confused because they're like, wait a minute, that doesn't go to 3%. But remember, 00, 01, 02, you just counted 3 numbers. Now the remaining numbers are going to be the ones that are non-birth defects. So 00, 01, 02 is 3% of the numbers. That would make this by default 97% of the numbers. And we can see that here if we start highlighting numbers, we have the 3%. Exactly. Great job, Lydia. And does this make sense right here? This is the 3% birth defects over here. And that's why I try to do the visuals right here to show this would be the 3% birth defects. And that's 00, 01, 02. And this would be the 97%. Thank you so much. And there was another one you wanted me to do, right? The lottery number one. I'm assuming you might have watched the videos for the other ones because I do have videos posted, and I might cut this out and put this as a standalone video. So a great job. Let's go click the question, get it right. We got it. So hopefully that makes more sense on why we use certain random number tables this way. We'd have to put all the commas here to help it make more sense. But random number tables are a way to generate random numbers, or we could use sites like random.org, but we can also generate our own random numbers. And we are using 00 through 99, 2-digit number combinations, where 3% of the numbers are assigned to babies born with some kind of birth defect, and 97% the remaining, which we see right here, visualized, 3%, 97%. Awesome. Okay, let's do the next question here. The next question was lottery, right? Because I'm probably going to cut these out because these are tough ones, and understanding how to do them and assigning random numbers is key. So let's go to the lottery one. This one's tough. I've already got a video for this one. I've already got a video for this one right here. So is it this one? This is a multiple choice one. I think this one right here is pretty crazy. As I hit the, once you gotta do the state one's pretty easy. I think it's this one right here, right? If you confirm, we'll do this one. We'll put this into a video and I'll teach in photo minutes. Gotta reset the computer. Is this? We'll see if this is the problem. Sorry, no one can see me. But you know what you can see? You can see Puppet Shark. Puppet Shark. I destroyed the video today, Puppet Shark. Tiny Brian's not there. It's so funny when I turned this on today. Tiny Brian was there, and because we worked on it yesterday, I think. Is this the one, Lydia, that you're thinking of? I think it is, because you mentioned, let me double check up in the chat. I think you mentioned a lottery one. Babies born with birth defects and lottery with lucky number 1. Is it? There's a different lottery one. This one's more difficult. This is probably one of the toughest problems right here, just theoretically to understand it. It's about a website called Lucky Numbers. It might only be on the homework. Let me go look at the homework. Okay, let's pull up the homework, unless it's the first question. Okay, let me go grab the homework assignment. I bet it's only on the homework. I know which one you're talking about, I think. And we'll do that one. And thank you for hanging out while we did some 320. Dude, wait, I can't find it. I swear it exists. It's about a website called Lucky Number. It's on the homework. Oh, it's this one right here? Okay, good. I was like, okay. Okay, good. Take a multiple choice, and you have to say a number four. Number four. I had already passed. I was like, that doesn't sound like it. Okay, here we go. So let's talk about this one. So this one right here is about basically trying to win the lottery, and apparently the lucky number is 1. So what proportion of the time do you win when we simulate numbers between 0 and 9? Now we have here 60 random numbers, and let's go ahead. We're going to copy paste this, and we're going to make our lives easier. I think if we increase the font, it might help. Can I get it to wrap around the screen? That's my goal. That's big enough though. So we're going to take these numbers and we're going to copy paste them. There we go. We got the numbers. Let's go over to our 10,000 word documents. Now we have 10,001 word documents. And here's our numbers. Now be very careful because I have missed one of these numbers. We want to know out of these 60 numbers. And so we're estimating the probability of winning with this simulation, where if we get 1, we win. Let's go ahead and start counting the ones and hopefully tell me if I missed one. I'm just highlighting the ones. The reason they put some spaces right here, random numbers sometimes give you spaces between the numbers to help make it easier to see them. So they're in groups of 5, but it doesn't really matter. They're just making it easier to kind of notice the difference. And you are correct. We're just going to divide the amount of number ones there are, which there are 6 of them. There's 6 here total, 6 ones, divided by 60, and this is going to tell us that there is a 10% probability. It might want it as 10%, so make sure to put it in however it says for decimal or for percentage. And let's see, it wants as a percentage, and I was like, wait a minute, I recall. There we go. Did you have any other questions? So once you know that one's pretty simple right there. Was there any other questions you had on any of these? We just got a little more time right here. Next class, Stat 201. Yes. Look at my phone right there. I got to plug in my phone. Losing power. The randomness quiz and homework are pretty... Oh, no, it's so easy. I've done it. I've worked that question with students and been like, I've been like, wait a minute. I think I got this wrong. Oh. You ever plug your phone in and it doesn't start charging and you're like, wait a minute, and then you look and the cord's unplugged? No. There we go. Oh, I think that's got it. I'm going to go over to space here. I'm not going to be here. No, Brian. You know, who's running? It's been Mubot all day today. All day today, it's been Mubot. Mubot's been running the show. I need a Mubot button on the front of this so I can easily talk to Mubot over here. Mubot, you've been running the show all day. There's been no Brian. With that, everybody, we'll put on a little chill music as we usually do. We did a lot of 320 work. Got a little 201 work done. 201 will have class here soon in about 35 minutes. You're welcome, Lydia. Thank you so much. Great job working ahead on these assignments. I think you and many others did great on the test. I don't want anyone to be discouraged by their test grade. I understand it's a little difficult of a test. You're welcome, Kayla. Excellent work. Thank you so much. And I love it when people are just hanging out, and it's always nice to say goodbye to everybody. But we will be back, and keep working hard. Anytime you're stuck, just ask a question. You just wait for office hours or every day. So swing by here, and I think a lot of people know that. Just swing by, ask the question. I'm probably going to give a bigger answer than the direct answer, but that hopefully we can learn some concepts while we go through this and make sure we understand why it applies and how to do it. That way, if we get a new question that isn't the exact question, like when we get to the test, you're like, okay, wait, Brian said these extra things right here. That's how it works. I'm snapping my fingers. But I will see everybody, and you will see me soon. I will get the webcam fixed. Not the webcam, but the camera, the 4K camera from the Haslam studio here at the University of Tennessee, Knoxville. Bye, everybody. Bye.